All right, so remember there's an SI tonight. Not tonight, right after class, in fact. Over in Old May 115. Okay, time to stop talking. Got some UTF office hours tomorrow. We got homework 3 going on due Monday night. All right, so we've started into this chapter on organic chemistry. We introduced some functional groups. We learned how to name linear alkanes and alkyl groups, and then last time we spent a bunch of time naming branched chain alkanes. Okay, so we know everything we'll ever need to know about naming. Okay, too much talking, please. Branched chain alkanes. All right, so what we're going to do today, we're going to spend some time looking at the dynamics of alkanes. All right, so we draw all these molecules, we draw them various ways, but they're always stuck on the sheet or the board or whatever. But we're going to talk about what they actually do. Right? So we're going to spend some time doing that. If we get through that, we'll learn a little bit about cycloalkanes, about naming those, and then we're going to go. Probably not all today, but go into much more depth about one group of cycloalkanes and how they can flop back and forth and things like that. Okay? So, all of this stuff about what are called conformations, we'll talk about that in more detail, that plays a role in both of these. This is one of those places those little model kits can help you as well. Okay? So we've done all of these functional groups, and now we're going to talk about alkanes. Okay, so let's just start with ethane. All right, so we've seen various ways so far we can draw the structure. But what we really want to do here is consider this in 3 dimensions. Okay, so if we want to draw an organic molecule in 3 dimensions, what do we have to use? What kind of bonds do we draw? Or what kind of designations do we do to indicate that it would have some 3-dimensional shape? All right, we're going to use some wedged bonds and some dashed lines and things like that. So let's go ahead and just thinking about. I'm going to do this again in another slide. Draw one way to do this. I don't want to use green right now. Okay, so we might draw an H like this. We have a wedged bond like this with an H. A dashed bond. Okay, so what's, I guess I didn't ask, what should be the geometry around these carbons? Tetrahedral, right? What's the hybridization of the orbitals on the carbon? sp3, that's right. So let's just do the same thing on the other side then. All right, so what kind of a bond is this? It's a sigma bond, right? And what did we say? What's the characteristic of sigma bonds? They're cylindrical, right? So there's no directionality to them at all. And so what that means, because they're cylindrical, we can rotate around this bond. All right, so we could take one of these methyl groups and spin it relative to the other, kind of like it's a spinning a propeller or something like that. All right, and so this is going to give us several different structures depending upon the orientation of one end versus the other. Okay? And we're going to generate what we call conformations. And these are going to be different structures that are different based only on rotations around single bonds. Okay, so they differ only by rotations around single bonds. Okay, so let's consider this more deeply on. Okay, so I'm just going to redraw what we had just a minute ago. Basically, okay, here's one end. Each one should be a tetrahedral. But how did I know, for example, on this one, how did I know or how did I decide that these two hydrogens would be in the same, well, that I just draw them both with single lines and not wedges or dashed lines? There's a certain reason why I would do that? No, not really. It's completely arbitrary so far. So in this one, these two hydrogens, or the carbon-hydrogen bonds, are in fact actually this hydrogen to carbon to carbon to hydrogen. These are all being drawn in a single plane, right? So this is all in a plane. Okay? So what can we come up with, though, if we rotate around this bond? Okay, so let's say we're just going to rotate this by 60 degrees. I'm going to go like this. We're going to rotate by 60 degrees, and we're going to end up, I'm going to keep the left carbon the same, and I'm rotating the one on the right. So I'm going to have it like this, and now, so this one is going to rotate back this way, this is going to go part way, so I'm going to end up with a structure that looks like this. Okay, so I've just kind of changed where the wedged bonds are and the dashed line bonds are. But notice that now the hydrogens that are in a plane are the ones that are on opposite sides, right? So these are in the same plane. Okay, so all I've done is just kind of rotate one of these a little bit. Okay. So we could say, for example, let's say that this hydrogen that I'm circling here, I just rotated a little bit down, so it's now in the plane, right? The one that I rotated, that I'm circling here in red, has rotated up to here, and the one that we'll do in blue, this is circled in blue here, is just rotating over a little bit this way. So I've just like turned it just a little bit. Okay? So these two structures are in fact conformations of one another. Okay? They differ only in a rotation around that single bond. Okay? So let's look at of drawing these kind of structures. All right? So here's the same structures. I guess I have them reversed, it looks like. The same two that I had a moment ago. And we're going to do a certain kind of drawing called Newman projections, and these are good at kind of showing the angles between all the bonds. All right? So what we're going to do is we're going to draw it like I was looking at this carbon-carbon bond end on. Okay? So I'm just kind of like putting my eye right down here, and I'm going to look straight down that carbon-carbon bond. Okay? So the way I'm going to draw this is I'm going to draw a dot for the carbon that's in front. Okay? One carbon is going to be right behind the other. All right? In fact, here, let me pause just for a second. I'm going to show you this in a different way. Maybe tomorrow I'll bring my little model kit, but I didn't bring those today. So let me. Okay, so the way I'm going to do this is that the carbon in front is going to be drawn as a dot. all right? And then I'm going to draw all of the hydrogens, but we're only seeing it from the front, right? So one of the hydrogens is going to go up, all right? So that's the one that's going up. And then the other ones, no, remember on the other program, they essentially going to look like a triangle. And so this one's going to come out this way, and this is going to come out this way. Okay, so this is the carbon in front. Now, because the carbon in back is hidden behind the one in front, we're going to cheat a little bit. I'm going to draw this in a different color, and the carbon in back we're going to draw as a circle. Okay, so in back, so this is the carbon in back. The blue one, where should I do this? Let me label it afterwards. Okay, so the one in back, the hydrogens are just staggered from the ones in front. So here's one, and here's one. Okay, so in the blue is the carbon in front. Okay, so notice that one thing that we have to be very careful of when we draw these structures is showing that 3 of these bonds are all going just to the circle, and 3 of the other 3 are going all the way to the dot in the middle. Okay? You have to designate where they're going. If you draw all lines just to the circle, or I can't tell which ones are going to which, then you'll get it wrong on the exam. Okay? So you got to be very careful on how you draw these. Okay, so this one is what we called staggered. Okay, because the bonds are off to the side from one another. All right, so let's do the same thing for this other structure. Okay, here, we're going to look right here, peer down this. I'm going to do it just the same. So the front carbon is just the same, right? So we do it, oops, I did that wrong. Draw it with a dot. Like this. So here's our one in the front. And then in red, I'm going to do the one in the back. So how is this one going to be different than the other one? Well, the hydrogens are going to be right lined up, right? So we're going to cheat a little bit here. I can't draw it right behind it, so I'm going to offset it just a little bit so we can see it. Okay? But what we're trying to show is one's in front of the other. Okay, so this one, the name for this type of structure we can think of if we think about what happens if the say the moon gets right in front of the sun. What do you call it? Eclipsed, right? It's an eclipse. So here we have one hydrogen right in front of the other, so this is called eclipsed. Okay, and these are conformations of one another. Okay, they're only different in how we've rotated around the bond. Okay, so what do you think? We have these two possible structures, these conformations. Okay, we have the staggered. This is how my computer draws it. Eclipsed. All right. So do you think one of them is going to be more stable than the other? Staggered is going to be more stable. Why is that? Right, the energy's lower. That's not really a why, though, right? That's another statement of it being more stable. Right, everything gets farther apart, right? So actually there's a couple of different explanations here. And the book, when it went into this 7th edition, changed their explanation for this. Okay? So let's say why. And we'll say that the old explanation is that the electrons in those bonds repel each other, right? And so they just orient so the bonding electrons get as far apart as possible. Okay, so we have electron pair repulsion between bonding electrons. Okay, and I think this is a pretty intuitive model for why this happens. They just, they're going to just kind of rotate around, and they're going to kind of find their place where they're as far apart as possible. Okay, but the book says that's not really the correct explanation. Okay, it works, but it's not really right. Okay, so the new explanation that we're going to actually use, okay, is more complicated. All right, and it has to do with something called hyperconjugation. All right, we're going to see this concept a couple of times in class. And what it essentially means is, let's see, let's look at this. I'm going to draw this out again from the side. Okay, and I'm not going to draw that carbon atom this time. So here's an H and here's an H. And if I draw this other H, other carbon-hydrogen bond, what type of an orbital on the carbon is being used to form this bond? Kind of said this already. sp3, right? So I'm going to draw that. Here's our sp3. I'm just going to do it all in one color. And this is going to the hydrogen, and it's 1s orbital. Okay? That's just the sp3. That's just the sigma bond. Okay? On the other side of the more stable one, we're going to look not at the sigma. So this is a sigma. But we're going to draw out what would be this sigma star. So what does the sigma star represent? Or what is it? It's the antibonding orbital, right? Here, let me do this better. Okay, so let's see. I'm going to do this a different color. How would the sigma star orbital for this bond right here be oriented? Does it orient right down into this bond, the antibonding one? No, it goes to the opposite side. They point away, and there's a node in the middle. Okay, so the antibonding one is going to look more like this. And then it has an orbital here. And I haven't really drawn the colors, the phases of that, but this is the sigma star. Okay, so it's anti-bonding. So the concept is here that there's 2 electrons in this sigma orbital. How many electrons are in the sigma star on the other side? 0. None, right? Because every time we did those molecular orbital theory tables, we always put 2 in the bottom and none in the top. Right? So the sigma star is empty, but what can happen is that this sigma orbital can donate a little bit of electron density into the sigma star. So there's a little bit of an interaction between those two, and that creates a little bit of an attractive force. So instead of being a repulsion that's holding these apart, there's this hyperconjugation, which is an attractive force between this sigma and this sigma star. This sigma would be to another sigma star over here. This one here would be to another sigma star here, and backwards the other way as well. Okay, so there's this little thing of sigma to sigma star. We'll just call this an overlap, or donation. Okay, and this is just a weak attraction. Okay, so what they've kind of done is take this, instead of being a negative thing, a repulsion, they've made it into something positive and saying it's actually an attractive force. And this sigma to sigma star overlap only happens when this sigma bond is in the same plane as the sigma star. Okay, and that only happens when we're in this in this staggered conformation. Okay, so this one is more stable because of this hyperconjugation. In the eclipse, they can't have any hyperconjugation. I know, this is kind of more complicated. I kind of like the old explanation. Okay, staggered is more stable than eclipsed. Okay, so what happens if we just rotate one around the other? Okay, so here's a graph of the energies. All right, so we're going to start out, we're going to look at what's called a dihedral angle. Oops.
Can I ask a question?
Yes, of course.
You probably talked about it already, so I think know what you're asking. But how come when it's staggered, does the sigma bond turn into sigma star bond? Or I'm sure you.
Oh, okay, so the question is, why does the sigma turn into a sigma star? It doesn't. Okay, at any time when we bring together the two orbitals and we make our molecular orbitals, remember we mixed them together, we made one that was lower in energy and one that's higher in energy. Okay? The sigma orbital is where the bonding is taking place. So even the bond that I showed where the sigma star is, there's a sigma bond there that's holding the carbon to the hydrogen. But there's also the sigma star is kind of superimposed, but in a different orientation. So that's just an empty orbital that's lying in that same plane. And because it's empty, it's a place where electrons can be donated into. Okay, the sigma bonds, the sigma orbitals are filled, holding the bonds together. Okay? But some of the electron density in the sigma bond if it's in a plane with a sigma star that's empty, it can donate just a little bit of electron density, and that creates an attractive force.
So the reason why the bottom two sigma bonds don't kind of attract to each other, because on the other picture that you showed, there's a little circle that you have, but you put like a big circle on the opposite side to show the sigma star bond. Why don't the two bottom parts of the sigma star, do they attract each other as well?
No, the bottom parts of the sigma star, that's all one orbital. Okay, so one orbital can't attract itself.
Okay.
All right, so it's like in a p orbital, there's two lobes of the p orbital, right? In the sigma star, there's actually three different positions that have some electron, that could have some electron density. So just a different shape of an orbital. Okay? I know it's kind of a more abstract concept here that they kind of inserted for us. So this is, we're going to look at the dihedral angle. Okay? And what the dihedral angle is kind of the angle from one hydrogen to a carbon to the next hydrogen. So it's the angle between these two when we're looking at the Newman projection. So for example, if we look at these two hydrogens that are in red, one of them is directly in front of the other, and so the angle between those two, what do you think would be the angle between them? If we weren't cheating it just to the side, if we were just saying one is right between the other, be 0. Okay, so this is a 0 degree dihedral angle. And what is that structure? Is it staggered or is it eclipsed? It's eclipsed. And so notice that the eclipsed is essentially at a high point in energy. And as we turn one of those, so it looks like we're turning the carbon in the back relative to the one in the front, right? So we're taking this one in the back and we're rotating it down. And so now we have this 60 degree angle, 60. And what do we have now? Is this staggered or eclipsed? This is, yeah, eclipsed. And then we have staggered. Right? And if we keep going, then we go back up to eclipsed, right? We keep just rotating it around another 60 degrees and we go to eclipsed. Another 60, we have these 180 degrees apart and another staggered, right? So we're just clicking our way around. And notice that if we have ethane, because it's symmetrical, same groups on both sides, we essentially have, 3 different eclipsed and 3 different staggereds that we can form. Okay? And all of the staggereds are higher in energy. Oh no, all the eclipsed are higher in energy and the staggereds are more stable, just like we said. Okay? Yeah.
So like I can see the highlighted carbons that you're drawing the 100-degree angle between.
Yeah.
Like global
The hydrogens, right? Yeah.
Yeah. So I can see how they're highlighted, but what makes those highlighted ones different than the other ones? Like why can't we go to the one that says 60 degrees and say it's 100 degrees between the top hydrogen?
Okay, so yeah, so they've highlighted one. It doesn't matter. Okay, so they're just highlighting one just so you can see that it's continually rotating. Right? We're doing a whole 360 degree. All that really matters here is that we have eclipsed and we have staggered, right? And they're both different in energy.
So are those 3, 60, 80, and 300, are they different energy levels?
The 60, 180, 300, no, they're exactly the same energy levels.
Okay.
Okay, they're not all the same. If we could have different hydrogens, they're each different. And what we'll see is if we put something, this is just a simplest scenario here, simplest compound that we can even do this on. If we put something other than hydrogens, we'll see that each of these rotations gives us something different, not getting the same thing back again. Okay? Yeah?
At 0 degrees, you always start with eclipsed, or?
At 0 degree dihedral is always going to be eclipsed because that means those bonds are all in line. Okay? Yeah, question?
So the highlighted hydrogens were actually a methyl group. The 180, the one at the bottom in the middle, would be the lowest energy.
Good question, and we're going to get to that in just a minute. That's like exactly the next thing that we need to do. Yeah, so the energies are going to be different for the different conformations if some of these groups are different than one another. Okay? All right, so the other thing I'm going to show you here is that if we look at the energy difference, so delta E, okay, it's listed right here, between the eclipsed and the staggered equals 2.9 kilocalories per mole. And what we're just going to say is this is about 3 kilocalories per mole, which means that it's essentially about 1 kilocalorie mole per eclipsed pair of bonds. Okay? So this is about 1 kilocalorie per mole per eclipsed bonds. Okay? If we just divide it by 3, we got 3 of them. Okay, so let's look at one that's step up in complexity. Okay, so we'll go to butane. So we're going to put a different group, a methyl group on each end. Okay, so let's just draw out butane. I'm just going to first draw it like this. CH3, the CH3 on this end, and then these 2 carbons, we're going to have a wedged bond, a dashed bond, wedged one, and a dashed one. Okay? And so what we're going to do is we're going to draw a Newman projection looking down the carbon 2 to carbon 3 bond. It doesn't really matter which end we draw it from here because we could count it from either end, but I'm going to count it 1, 2, 3, 4. And so we want to do a Newman down the C2 to C3 bond. Okay, so what this means is we're going to look right down this bond right here. Okay, so I'm just going to imagine, I can't really get up there, climbing up there and just looking down the bond. Okay? And what I should see, hopefully, is that the carbon in front, okay, has a carbon to methyl group bond that's going to be going straight down. Okay, so I'm going to draw it down like this. Right, and each one of these, because it's tetrahedral, is going to look like a triangle as we look down it. So the other two bonds, which go to hydrogens, one's going to go up this way, one's going to go this way. Okay, so then the carbon in the back, we draw it as a circle. I'm just going to do it all in one color this time, because it's probably how you're going to do it later. Is a circle for the carbon in back. And notice that this carbon bond is going in the opposite direction as this one down here. Okay? And so the carbon methyl group, this other methyl group is going to be pointing up the opposite way. And then I can fill in my other two carbon hydrogen bonds. Okay? So this is a drawing, a Newman projection of that structure up there at the top. So would this be staggered or eclipsed? Staggered, right? And in fact, this is a special kind of staggered because it has the two bigger groups 180 degrees apart. Okay? 180 for the bigger groups. And so we call this anti. Okay? They're on opposite sides, anti. Okay? Big, oops, what's going on here? Oh, now it won't do it. Big groups, 180. Okay, so now what I'm going to do is I'm going to rotate, which should we do, the front one or the back one? I'm going to rotate the back group. I'm going to rotate it down like this, and I'm going to rotate it by 60 degrees. 60. Okay, we'll do our little curly Q here. And so the front carbon is going to be the same. CH3s. So whenever you're doing this, you know, it's always better to keep one of the carbons in the same place and just rotate the other one. It just makes it less complicated. Okay, and then we got our circle, and then it's gone over 60 degrees, so we're going to have a CH3 here. We're going to have an H going down here, and we're going to have another H over here. All right, so is this one, this is eclipsed, right? Okay, let's do it again. I'm going to rotate this another 60 degrees, the one in the back. Okay, give my little rotation little thing. And so we'll draw it again. The one in the front stays the same. All right, the one in the back. We always know that if it's staggered, we'll still have these three bonds. Right, like that. Right, so where should I put the methyl group on those three if we rotate it down? On the lower right, over here, right? Okay, so this is again staggered. Right, do you think that this one is the same as the other staggered? Or are they going to be the same energy? No, right? So this one has to have a different name, and this one has kind of a weird name. So these are kind of getting close to each other, and this one has this name. It's Gouce. It's called gauche. Okay? This is the 60-degree angle between two groups on adjacent carbons. Okay? And when those get close together, okay, these are gonna get close, they are going to kind of repel each other. The atoms are going to start to get close to, they kind of bump off each other. And this is going to be called steric strain. Okay? All right, let's do one more here. Okay, I'm going to rotate this one down another 60. And let's see, where am I going to draw this? I'll draw it up over here. And so the first carbon stays the same. And the back one, now this is going to be hard to draw, has this other CH3 is right behind there. Something like this. Okay, so this one is eclipsed again, right? And do you think this is going to be the same energy as the other eclipsed? No, because now we've really forced those methyl groups even closer to each other. Okay? So we've created more steric strain. Okay, so let's take a look at these and let's see if we can rank what we would think about ranking their energies. So let's rank energies.
Hey, Dr. Biggs.
Yeah.
Not to be like particular or anything, just curious.
Mm-hmm.
On the second rotation you did, so you've got, okay, like what I'm looking for is when you rotated it, I would think that the CH3 on the carbon from behind would be on the other side of the hydrogen. Or does it not really matter? Are you just drawing it result?
You mean when I've done the eclipsed?
Yeah. So you're,
Yeah. So the question was, when I draw these eclipsed, does it matter if the one in the front is a little bit down or a little bit left?
Yeah.
It doesn't really matter.
Yeah, because I was just saying that on your back part.
Oh, right. I guess I have them both up like that.
Yeah. Does that
No,
not?
well, maybe it would be better if I did it the other way, but
But it's not like.
yeah, no. As long as we can show that they're kind of eclipsed. Usually I try to do that. I don't know how I slipped up on that. That's the first time that's ever happened. Okay, so which of these four structures do we think would be lowest in energy? The first one, right? This is lowest. Which do we think would be second? The other staggered. Staggered is always going to be lower than eclipsed. Because remember the last drawing that we had, it was going like this, and it was all the staggereds were the low points in energy, and the eclipses are always high points in energy. So they're kind of like transition states in this movement. It's never going to stop at the top of the curve. It's never going to stop eclipsed. Unless there's some other part of a bigger structure that really holds it there. Okay? So that's going to be the lowest. The other staggered is next. Which do you think would be third? The first eclipse, this middle one, right? Because those are eclipsed, but at least the methyl groups are farther apart, right? And the worst scenario is this one up here, right? Because we push the bigger groups closer together. Okay, so let's look at the graph, what we just drew. Okay, so they've just gone a little farther. And again, here, they're looking at the dihedral angle between the two methyl groups. Okay, so on the other one, they just had the red hydrogens. In this case, each one is actually different. Okay? So we start at 0, and like we said, when we have those two methyl groups pushed closest together, that's going to be the highest point in energy. Okay? As one of those methyl groups, now they're rotating the one in front, it looks like, rotates down, the energy goes down to a low point in energy. Okay, so we go again from eclipsed to staggered. It rotates again to another eclipsed for C, but notice that this eclipsed is a little bit lower than that highest energy eclipsed. And then it rotates another 60, and we get D, which we said was the lowest, because the two methyl groups are far apart. And then we essentially do the mirror image as we go back up. Okay, so it rotates to the other side. So notice that these two are the same energy. They're the two that have, you know, a methyl on each side is eclipsed with a hydrogen. Okay? And notice that B and F, these are the same. Those are the two that have, what was this arrangement here with them 60 degrees apart? What did we call that? Gauche. Okay, so those are the two gauche conformations, but it's gauche, one's just rotated to the right, the other one's just rotated to the left. Okay, and then A and A, actually those are, the two on the sides are actually identical, right? Because it's come all the way around 360 degrees. Okay, so we could have any different combination. We can have different groups on here. So let's look at, we'll finish off with one more exam. Undoubtedly on an exam, I'm going to give you the name of some structure. You're going to draw it out, and I'm going to tell you to draw Newman projections for looking down a certain bond. Okay? And I may ask you to draw the lowest energy staggered and the highest energy eclipsed, or the highest energy staggered and lowest energy eclipsed, or some combination of those things. Okay? So in this case, let's we're going to do this on 2-methyl-butane. Okay? And let's see if we can just do the highest, well, let's find the lowest energy first. Okay, so let's just draw the structure. Butane, like this. I kind of like to put these, when we're rotating it around a certain bond, I like to put those methyl groups, so then when we draw it in the structure, we can see them. And we're going to do this around the C2, C3, like we did as before, and then we can count 1, 2, 3, 4, and it's 2-methyl, right? So on that second position, we have two possible bonds, right? One has to be a wedge and one has to be a dashed line. So if this is all the information I've given you, you could start with either one, all right? And it would be fine. I'm going to arbitrarily choose to draw my wedged line with the methyl group and the H and the dashed line to my H. Okay, I could do it the other way and you'd be fine. Okay, so now I want to do a Newman projection looking down this C2, C3 bond. Okay, so we're going to do just like we did before. So we're going to draw the front carbon as our dot. And we have a methyl group, again, going down. Okay, my head was up on top there, going down. And then we have two more bonds. Okay, for the structure that I have drawn, should the methyl group be going to the right or the left? To the right, right? So, right. So if I'm up there looking this way, I'm looking down on it, the other methyl group has a wedge, so that's pointing out of the plane, right? So it should be going to the right. Okay, if I chose to draw the methyl group as a dashed line, these would just be reversed. And you would essentially get the same answer in this case. All right, so then the one in the back, right, it's just like before, has a CH3 up and 2 hydrogens. Okay, so notice what we have is, if we look at the methyl groups on the back carbon relative to the ones in the front, we have one pair, which is gauche, and we have one pair, which is anti. Okay. So do you think, is this out of the possible staggered conformation? So we can do, let's do another staggered. So if we're going to do another staggered conformation, we would rotate it 100 and one of them, let's do the one in the back, 120 degrees. So back by 120. So I'm going to keep the one in front like this. And the methyl here. H over here. Circle for the one in the back. So I'm doing it by 120, so the methyl is going to go over to where this H is, right? And they're going to all change places. They're all going to kind of ratchet over one position. So now I have the methyl group here, and an H over here, and an H over here. Okay, so which of these two structures do you think would be lower in energy? The first one, right? Why? Because it has one of the relationships is anti, the other one is gauche. What does this new one have? Right, there's two. This one is gauche, and this one is gauche as well. Right, so this one would be lower energy. This one would be higher. Okay? So we could draw eclipsed conformations as well, and we should be able to look at and analyze which one has the more steric strain and which one has less, be able to compare them and rank them. Okay, so a good thing to do is for any of these structures, and there's examples like these on the old exams, is to just go and just draw every one of those and, analyze them. Okay? So I will see you guys tomorrow morning.